Hi, I'm going to pick up with an example that we've seen before of observational data based on defective parts and location. Okay, um, and I'm going to discuss a few rules of probability. Okay, one of those rules is going to be the complement rule, the general addition formula, and the conditional probability formula. Okay, so the first thing I'm going to discuss is called the complement rule. And in a previous video, we have calculated all of these probabilities. The probability of defective overall, regardless of location, the proportion of parts produced at location 2, and the probability of, or proportion of parts that are defective at location 2, i.e. probability of location 2 and defective. I'm going to calculate probability of location 1. And from this previous activity, you know, it's just, it doesn't specify defective or working, so it's either of those two. There's a total of 800 when you add those two at location 1, and the probability of a part is produced at location 1 is 800 out of 1500. And you should notice, hey, we could have guessed this based on the probability of location 2. The relationship would be 1 minus the probability of location 2, and that would simply be 1500 over 1500 minus 700 over 1500. So the formula, or the rule, is as follows. The probability of a complementary event, because the opposite of location 2 is location 1 and vice versa. So the probability of A complement is 1 minus the probability of the event A itself. And that's the complement rule. Okay. I want to calculate one other probability. What's the probability of defective, or, and here's the key qualifier, we've seen the qualifier and, but now we have an or, location 2. So this means one or the other needs to be true. So location 2, that's what we have here, or defective. Okay, we have the condition defective being true at location 1 with 175 parts. Remember, only one of the two conditions needs to be true. So that will be the 175. Now we have defective and location 2. That's 125. Both statements are true. Okay, then we have location 2 being true, but they're working. Okay, that's fine because only one of the two statements needs to be true, and it's that it's at location 2. That's 575 parts. Divided by 1500. And what you're going to see is, you might wonder, hey, what happens if I take probability of defective plus probability of location 2? What do I get? Well, location 2, let's work out this one at a time. Probability of defective would be 300 out of 1500. Probability of location 2, that will be a 700 out of 1500. and you get 1,000 out of 1,500. That's too much. That's not equal to this number. And, in case you're wondering what this number is, let's calculate it. That's going to be 875 out of 1,500. So it looks like the formula I wrote down is off by 175 parts. Okay, I'm going to scroll up. 125 parts. I'm going to scroll up. Hey, look. This probability of location 2 and defective, that's exactly 125 parts. This number right here, right? So it looks like I can account for that missing information. What if I subtracted by the and of defective and location 2? So I subtract by 125 out of 1,500. Then both sides are equal. And this is the statement of the general addition formula. It says the probability of two events in an OR outcome, probability of A or B, is just probability of A plus probability of B, and then subtract what they have in common. Subtract probability of A and B. And this is the general addition formula. Okay, let's go over one last example. Suppose I know where a part comes from. So I know that the part I got was from location 2. Okay. I want to know the probability of defective, given it comes from location 2. Okay. So another way of writing this, and I'm going to shorthand this, probability of defective, this given is sometimes written with a bar for mathematical notation like that. Given location 2. Well, I'm going to shorthand this further, and we're going to calculate this with the formula for observational probability. Okay, so probability of defective given location is 2. Okay, let's go up to our data, because that's how we have to calculate it, right, with this observational probability. So how many do I observe that are defective given they come from location 2? Well, it's only 125. You might ask, well, what about the 175? Well, I know it comes from location 2, so it's only the 125. So I have 125. Okay, we need to divide by the total number of outcomes. Is the total number of outcomes 1,500? No, not in this instance, because I know that these parts need to be associated with location 2. So the only outcomes associated with location 2 are 125 plus 575, which is 700. Total number of outcomes is 700 for location 2. So that is the conditional probability that it's defective given location 2. Okay, hey, that 125, that looks pretty familiar. That is the number of defective and location 2. That 700, that looks familiar. That's the probability of location 2. So this is the general formula for probability. In fact, I'd write this, if we were to calculate these probabilities, you might say, what happened to the 1500? Well, you get 125 over 1500 divided by 700 over 1500. Then they cancel and you just get 125 over 700. And we calculated this n probability here. We calculated probability of location 2 here. So we have all these numbers previously calculated. So you might ask, what's the general formula? And this will be for A given, another keyword will be if or when B is true. Okay. And this will be probability of A given B. Mathematically, this is also written as A bar B. So it will be probability of A and B divided by probability of B. And this is the formula for conditional probability. One last thing to note is that things are called independent. Let me rewrite this. So two events, A and B, are independent if probability of A given B is just equal to probability of A. There's an equivalent formulation which would be probability of A and B equals P of A times P of B. So for independent events, you can just multiply them, and that's nice. Okay. You might ask, is probability defective independent of location? That is, it doesn't matter which location I pull things from. And hey, we have this probability of defective, and I'm going to shorthand this by 2. That's going to be this 125 over 700. Is that independent of location 1 or 2? And I apologize, I made a typo. This should be given with the bar here. Is that just equal to probability of defective, the overall rate of defective? Or does it matter which specific location you pull apart from? Well, probability of defective, we calculated that. Probability of defective, that's 20%, 300 out of 1500. That's the overall rate of defective. For location 2, it's 125 out of 700. And that's 18%. It's lower. So in this case, these two are not equal. So no, defective and the location are dependent, meaning the probability of defective changes by location. And the question statistically is, yes, these numbers are not exactly equal. It's 18%. This number right here is approximately 18.1% versus 20%. But what if it was 19.8% versus 20%? Would that be close enough? And you need to answer that question with probability. How close is close enough? Because there's randomness in the data. I think if we got 18.9 versus 20%, we'd agree that's close enough. But 18 versus 20, that's about 2% off. I'd be willing to guess that there are differences based on location in this instance. Okay. So just as a recap, I gave you a bunch of formulas. So one of them is independence. There's two equivalent formulations. I gave for you conditional probability, you have the general addition formula, and you have the complement rule. You're welcome. Thank you very much.